Hello everyone, my name is Ortolá-Leonard, and I'm a graduate student here at the University of Florida, working with Cahn and Slepian in modeling the Redshift-Space galaxy 4-point correlation function in the event parity sector. However, I will show you by the end of this talk that this model is also going to be important to understand the parity-odd sector. So let me start by the very beginning by introducing you to the 4-point correlation function. Then I will follow by showing you how we model the 4-point correlation function, then followed by the results of our analysis. And then in 4, I will try to show you what we plan to do with this model and how this is going to be important for the parity-odd sector. So the 4-point correlation function is the access probability over random of finding 4 galaxies in a specific tetrahedral shape, which mathematically we can describe as the ensemble average of the product of 4 galaxy over densities minus the contributions from pairs of galaxies in our tetrahedron. And the galaxy over density term I'm going to use interchangeably with the term density contrast for reference in future slides. So modeling the 4-point correlation function in real space is a very difficult task to do. So what we do is we go to Fourier space where we have the 4-point correlation function counterpart known as the trispectrum, which is defined in the circle, in the blue circle here. So what we do next is we are going to expand the density contrast in a perturbation theory series, which allows us to find the 3 terms that we have here up to order of density contrast to the 8th power. And so if we look at the first term, what we find is basically that we have a product of 4 first order density contrast, which the first order density contrasts are going to be Gaussian random fields. And so these Gaussian random fields, if we use Wick's theorem on them, is going to allow us to split them in products of power spectrum, which means for us, since the power spectrums are well known, we don't want to study this specific term. What we want to study is the next contribution, which comes from non-Gaussian random fields in this case, and are known as the 3-level trispectrum. And so the first term here is denoted by the T2211 term. The red term here is going to be denoted by the T3111 term. And we can model what the density contrast in perturbation theory series look like by integrating some Redshift-Space kernels over some intermediate momentum variables, which the intermediate momentum variables are related to the original momentum variable wave vector k via this Dirac delta function. And then as you can see also, we include products of first order density contrast from K1 all the way to Kn, where the n is going to be equal to the order in our perturbation theory series. So just for completeness, also here I'm showing you what these Redshift-Space kernels look like. And as you can see, we have some bias parameters such as B1, B2, B3, and the tidal tensor bias. We also have some standard perturbation theory kernels such as F2, F3, G2, and G3, and where the F2 and the standard perturbation theory kernels are given by these equations. So if we now use this equation for the density contrast and we plug it into our 3-level trispectrum, what we end up finding is that after completing the integrals, is we have the T2211 and the T3111 term expressed in terms of products of the Redshift-Space kernels times power spectra. So what we did next is perform the inverse Fourier transform to try to find the 4-point correlation function. And so what we find is 17 equations that describe fully the three-level configuration space or the 4-point correlation function in the following format that I'm showing you here, where we have some constants that come from integration or decoupling some denominators. Then we also have radial integrals, which depend on the magnitude of the vectors R1, R2, and R3. And then we also have the isotropic basis functions, which is basically a combination of 3 spherical harmonics, as we can see here. Let me show you now some of the results for radial integrals for some of them. If we look at the leftmost part here, we have the radial integral for one of the vectors. In this case, Ri will represent R1, R2, or R3. And we have the integral over one spherical vessel times the power spectrum. If we look at the upper plot here for the black line, which represents the J equals 0 spherical vessel order and the power to n prime equals 0, we see that we can reproduce the 2-point correlation function as will be expected from this integral. Then in the lower plot, if we plug now J equals 2 and n prime equals 0, again for the black line, we see that we can reproduce the quadruple of the 2-point correlation function, but with a flip sign. And the flip sign comes because when computing the true quadruple power spectrum of the 2-point correlation function, we pick up a negative sign, which comes from the plane wave expansion going into the spherical harmonics. So this is why we see here in the positive axis instead of the negative axis, as will commonly be seen. Then on the right-hand side here, we have a radial integral, which depends on the 3 magnitudes of the vectors R1, R2, and R3. And this integral is given by intermediate integrals, which depend on 2 spherical vessel functions and 3 spherical vessel functions times power spectra. And as you can see, we have their plots here. So for example, for 2 spherical vessel functions, we have this plot. For 3 spherical vessel functions, we have this plot. And for the full radial integral, we have this other plot. And as we can see, the shapes are very different from each other. And so if you want to know why, I refer you to the paper that we're going to publish with the results, where in the appendices, we explain why each of these plots looks the way they do. So like why we have only behavior along the diagonal in this plot, and also being so narrow, or why this one looks like a rectangle, or why this one looks like an oval shape. With this, we arrive to our future work, where we plan to use the 4-point correlation function model to infer cosmological parameters such as the matter density and dark energy density. We also plan to do a VAO and RSD fitting such that we can measure the cosmic distance scale, and we can also measure bias parameters. But most important for this conference is going to be to compare our results against our fiducial cosmology. Because if we don't find any discrepancies, then we can conclude no systematics are affecting our 4-point correlation function, neither in the even nor in the odd parity sectors. So we can move into the parity-odd analysis. However, if we find any discrepancies, this will imply there are residual systematics affecting the two, not sensitive to the 2-point correlation function and 3-point correlation function, which are going to affect our 4-point correlation function analysis. Therefore, if we are able to correct for these systematics in the even parity sector, this will enable us to correct for these systematics in the odd parity sector, and therefore not reach any false conclusions in this parity-odd sector. So with this, I finish. I thank you so much for your time, and hope to see you all in the conference. Thank you.